Okay, so good morning everyone, and I'm Sir Jim, and I'm the cluster head of biology, organic chemistry subject. Okay, so for this session, we are going to talk about gases, which is the chapter 5 of your laboratory discussion. So we're going to do this asynchronously because we want you to have more control over your time since midterms week is fast approaching. So that means probably you are dealing with so many academic workloads. So it will be better if we just do this asynchronously so you can have more control over your schedules. Okay. So again, we are going to talk about gases, and I know that you are kind of familiar with this one as this has been discussed to you in your elementary, sorry, not elementary, at junior high school and senior high school subjects. Okay, but we are going to take a look into it, and we will have some refresher questions later to work with so that we can test if you really fully understand this session. Okay. So our coverage for this session today includes the following topics. So we are going to have an overview of what are gases and what's pressure, what are the gas laws that were observed by different scientists, and what's the relationship of density of gases with its smaller mass, gas stoichiometry, Dalton's law of partial pressure, and lastly, the kinetic molecular theory of gases. So, of all the elements in the periodic table, only 11 of them exist in the gaseous form, okay, such as hydrogen, nitrogen, oxygen gas, and your halogens, okay. So, other elements in the periodic table do exist in solid or sometimes in liquid form, such as mercury, okay. But for these elements here, they exist in the gaseous form. Also, not only these elements exist in the gaseous form, we also have the following compounds that also exist in the gaseous form, such as the hydrochloric acid, the carbon dioxide we breathe out, okay, and the nitrogen dioxide, sulfur dioxide, which are common pollutants in the air, okay. So all of them do also exist in gas form under normal conditions or 25 degrees Celsius. Okay. So by just looking at their characteristic, we can say that for gases, okay, the gases have the following characteristic based on observing these gases that I mentioned earlier. So we can say that gases assume the volume and the shape of their containers. So just like liquids, gases are fluid as well. So that means the particles of gas can flow from one another. Okay, so that's why if you place your gas in a certain container, it will not just stay in one position, rather it will flow around the insides of your container. So that's why we said that gases assume the volume and the shape of the container. Okay. Also, because of the interparticle distance in gases, we can actually compress them. Okay, so unlike solids, wherein the interparticle distance are very close, for liquids that's kind of similar also. But for gases, no, because they have very far interparticle distance, we can actually force them to be close to one another. So that means we can compress the gases. And apparently, of all the states of matter, gases are the highly compressible states of matter. So that's why gases are used primarily in hydraulic process. Okay, some of them use hydraulic gases in hydraulic process, and sometimes we use it in car tires, of course. So to inflate the car tire, we need to compress the gas particles there. Okay, so yeah, so gases are the most compressible state of matter, okay, because their interparticle distance, no, we can force them to be close to one another, okay, by exerting pressure. And also, gases mix evenly and completely when confined in the same container. So, unlike solids, no, when you place your solid in one location, it will not move unless you move it, okay? Or some external forces did the movement, okay? Pero for gases, okay, for gases, it just flows, okay, just like liquid. So that means um, when you place your gas in a certain position at your house, it will spread out. Okay, so that's why when your parents are cooking adobo, you can smell it because the air molecules, okay, that contains the scent of adobo, they can flow. Okay, and they can. flow from one room to another. So, yeah, so that means that gases do distribute themselves evenly in the space, okay, because of their great interparticle distance. And lastly, gases have much lower densities than liquids and solids, okay? So if you could remember, the density formula is mass over volume. So for gases, due to their interparticle distance, their volume needs to be very big, okay? So because the distance of the particle is very high, right? So that means they will occupy greater volumes with the same mass compared to solids or liquids. So that means gases do have very low density. Remember, if your matter occupies bigger volume, then your density becomes lower because of the inverse relationship of the two variables. Okay, and also the gas pressure exists because apparently the gas particles do exert force upon us. Okay, so remember in physics, okay, the force is the area to which your gas pressure is applied. Okay, so that's the product of area times the pressure. So that's the force. Apparently, gases also do that. Okay, so for example, in this picture, the gases here are exerting force against the box container. Okay, so from this equation, we can derive the pressure equation. So basically, you just divide both sides by A. So you get the pressure is equals to force exerted by the gas over specific area. Okay, and we know in the first law of Newton's first law, that force is equals to mass times acceleration. So that means when your particles hit you at a higher acceleration, then that means it will exert greater pressure. Okay, so the common units of pressure used in physics and in chemistry are the following. So we have the pascals, which is the SI unit for the pressure of gas, and we have the common unit called the ATM. Okay, so one atmosphere, and this is equivalent to 760 millimeters of mercury or 760 torr. Okay, and the conversion for Pascal and ATM is given as 1 ATM equals 101.325 Pascal. Okay, or in kilopascal, that's 101.33 kPa. Okay, so that's how we determine the pressure of gas. Okay, so the gases around us do also exert pressure upon us. Okay, so for example, our atmosphere. Okay, so your atmosphere is typically um, several kilometers thick, yan. So that actually extends to 100 kilometers. Okay, so the air particles inside that are also pulled by gravity. So that means the lower you are on the surface of the earth, okay, you will experience more gas pressure. So that's why in the surface, in the sea level, you will experience the greatest pressures in there. Okay, for example, you are standing here at the beach. Okay, so since you are at the sea level, that means the amount of air being compressed to you by gravity will be felt by you, okay, and that is actually equivalent to 1 atmospheres. However, as you go higher in terms of elevation, suppose you go to Baguio. So if you go to Baguio, your distance from the sea level is kind of far, okay? So it's, let's say, around 500 meters or so. Okay, so that means that uh, the gas the gas column above you isn't that many, okay? So hindi na ganun karami yung gas particles above you. So that's why the gas pressure at higher elevations becomes lower. Okay, so that's why as you go up to the mountain, the gas pressure decreases because the column of air also decreases with the increase of altitude. Okay, so that's why when you are in the Mount Everest, no, you cannot breathe with your lungs alone. Okay, so for you to breathe, you need to have your oxygen tank and nitrogen tank with you. Okay, because at these pressures, at this altitude, the pressure of the air is very thin, so that you may actually die of asphyxia. Okay, is that the correct word? So yeah, you can die of hypoxia pala. Okay, so you can die of hypoxia because there are so few gas particles around there, so that you cannot really breathe on your own. So you need to use external gas sources, okay, such as oxygen tank. Okay, so that's the idea. Okay, so as you go down to the surface of the sea, okay, sorry, the surface of the earth, as you go to the sea level, you will experience greater pressure due to the increased number of height of your air column above you. Okay, so the higher elevation you go, the lesser your air column above you. So that means the lower pressure is there is. Okay. So, in order for us to measure the gas pressure, okay, so we use barometer. So this is the barometer, and this is actually one of the simplest instrument that was used in the early times, okay, so around 16th century, in order to determine the gas pressure. So basically, this is just a vat of mercury, okay, and you have your inverted tube in which this end is vacuum, okay, and since we know that the gases above us do actually exert force upon us as they were being pulled by gravity, so that these gas particles will push the liquid. Okay. So again, since there is an external force that causes the liquid to move, okay, so instead of just being there, okay, they will start to travel across this tube. Okay. So apparently, at sea level, okay, the height of your mercury, okay, upon the pressure exerted by the atmosphere, apparently the height is about 760 mm, right? 760 millimeter. That's why we said that one atmosphere is equivalent to 760 millimeter of mercury. Okay, so that's the reason behind this conversion. Because apparently, when you expose this barometer in the atmospheric pressure, the mercury increases its height to 760 millimeter. Okay. So suppose you're doing chemical reactions, how you're going to measure the pressure. Okay. So in doing chemical reactions and you want to measure the pressure exerted by the gas formed by in the reaction, you may want to use the manometer. Okay. So the manometer looks like this one here on the right. Okay. So this is the vessel wherein you can do your chemical reaction. And as gases evolve, you can actually determine the pressure exerted by the gases because the elevation of the mercury levels here will be different. Okay. So the height difference of these two mercury levels can give you an idea on the gas pressure exerted by the chemical reaction. Okay, so those are the ways we can determine the gas pressure. So if you're doing it outside, okay, if you're going to measure the atmospheric pressure, you will need to use barometer. While in chemical reaction, we usually use the manometer. However, due to health concerns, I think that this methods doesn't work anymore. Okay, because mercury is, as you know, toxic. So some laboratory experiments do not actually use this anymore. Rather, they use other instruments such as ebullioscope meter, something like that. Okay, so yeah, so they don't use mercury chemicals at all. Okay, because these are toxic substances. Okay, so now, just like in your high school, let's have a review on the observed behavior of our gases depending on different parameters such as pressure, volume, temperature. Okay, so these are the scientists that actually contributed to develop the gas laws, and all of them were discovered at a different time. Okay, so basically, so we started with the Boyle's law. Okay, and followed by the Charles law and the Gay-Lussac law. And then once we discovered all those three, we were able to combine them to form the combined gas law. And then Avogadro made his own law, and then we arrived with the ideal gas law. Okay. So again, so these gas laws are just the observed behavior of different gases as you subject them to different pressures, temperature, or volume. Okay. So, this has been studied in the end of 18th century until now. Okay, and these gas laws still hold true until now. Okay, so assuming that the gases you are studying are ideal. Okay, so let's begin with the Boyle's law. Okay, so Boyle's law is called the PV relationship of gases, wherein the pressure and the volume all have some relationship. against one another. Okay, so according to this statement, so Boyle's law states that the volume or the fixed amount of gas is inversely proportional to the pressure applied to the gas. Okay, so if you graph it, it looks like this. So in the y-axis, you have your pressure here. On the x-axis, you have your volume. As you can see, as the volume increases, the pressure of the gas decreases. Okay. One way to think of this Boyle's law is to look at how we actually breathe. Okay. So when our chest, okay, when our chest, or let's say our diaphragm relaxes, what happens is that the pressure inside the lungs increases. Okay, and that causes our lungs to shrink. Okay? However, when we inhale, okay, so when we inhale, our body actually loses the pressure. So as it loses the pressure, our body will need to suck in the air through our nose, so that the lungs will be filled out. Okay, so that's one of the application of the Boyle's law when we are breathing. Okay, so again, when our diaphragm relaxes, the pressure increases inside the chest so that we exhale the gases. Okay, because we want the volume to be decreased as the pressure increases. Okay, however, when we inhale, okay, our diaphragm expands, so that means the pressure inside the lungs decreases. That means also that you need to increase the air volume inside your lungs, so you breathe in the air. Okay, so in equation form, okay, since it is inversely proportional, so we can write that relationship as P proportional to inverse of volume. Okay, so again, how to read this? This is the pressure inversely proportional to the volume. The symbol here is called the proportionality symbol. Okay, and just like in algebra, okay, this proportionality symbol can be converted into a constant, so we can get P is equals to 1 over V times the constant. Okay, K is the constant. And then we can just transpose it to the other side, and we will get this uh, equation. So PV is equal to K. So suppose we have two states. Okay, so the initial states. So the product of pressure and volume at the initial state is equal to a constant. And let's suppose we also have the final state or the second state. So the pressure and the volume at the second state, when you multiply them, it is also equal to a constant. Since the constants are equal, then we can combine them to form this equation. P1 V1 equals P2 V2. Okay? Wherein the ones are your initial state and the twos are your final states. Okay? So again, we just derived that from this relationship. Okay? And we know that constant is still constant regardless if it is the initial state or the final state. Okay? So that means you can combine them. Okay? So by combining them, you get this equation. So let's apply the Boyle's law in one of the word problems here. Okay, a sample of chlorine gas occupies a volume of 946 ml at a pressure of 726 millimeter of mercury. What is the pressure of the gas in millimeter of mercury if the volume is reduced at a constant temperature to 154 ml? So first thing that you have to do is to determine the given, of course. Uh, Initially, on the first statement, you are given 946 ml as your initial volume, okay? And your pressure initially is 726 millimeter of mercury. 726 millimeter of mercury. Now, in the second sentence, you are given the final volume, which is 154 ml. So you are asked now to determine the final pressure, okay, after the volume was reduced to 154 ml. So we know that Boyle's law is P1 V1 equals P2 V2. Since we are looking for the P2, we need to divide both sides by V2. So we will get the equation P1 V1 over V2. So now we have all the givens. Okay, so what we're going to do is just plug in all the numbers. So P1 is 726 millimeter of mercury. Volume 1 is 946 milliliters. And then your second volume is 154 milliliters. Okay. As you can see, our volume units cancel out and we are left with the millimeter mercury unit. So that means our calculation should be correct. Okay. So let me just type it into my calculator. 726 times 926 divided by 154. So the final answer is 4,459 millimeter of mercury. Okay. So as you can see, if you need to decrease the pressure, sorry, if you need to decrease the volume to 154, you need to apply that much pressure. Okay. So yeah, as you can see, the Boyle's law holds true that when you increase the pressure, the volume decreases. So that's why Boyle's law is called the pressure-volume inverse relationship. So now let's proceed with the next gas law, which is the Charles law. Okay, so Charles law is called the volume temperature relationship. Okay, so in this diagram here we have the volume and the temperature curve. Okay, as you can see, when the gases in here are heated, okay, that means the temperature increases. What happens? The volume of gas increases as well. Why do you think that's the case? Okay, because we know in your lecture video that our gases, okay, our particles do have uh, kinetic energy, right? So by increasing the temperature, increases the that increases the thermal energy of your particles, and the thermal energy is being converted to kinetic energy. So that means by increasing the temperature, the kinetic energy of your particles do also increase. So as they hit the 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 top part of this piston here. So since they have enough kinetic energy, that means they can actually push the top of the container, making the volume expand. Okay, so yeah, so that's the reason behind this Charles law, the pressure volume temperature relationship. And again, the relationship is direct, so the proportionality equation should be written as the volume is directly proportional to temperature. Okay, so keep in mind that if it is a fraction, that's inverse. But if it is not a fraction, that's direct relationship. And just like what we did earlier, so this proportionality symbol can be converted into equality by introducing a constant k. And let's divide both sides by t, so you will get this equation here. So at initial state, v1 over t1 should be equal to k. Okay, so this is at your first state. However, at the final state of your change, okay, if it reaches this volume here, if you divide v2 and t2, you will still end up with the same constant. Okay, and again, constants are constants, so that means you can combine them, and that will give you the Charles law equation. v1 over t1 equals v2 over t2. Okay, so that will hold true provided that the pressure is maintained constant and the amount of gas is the same. So let us apply the Charles law in this type of problem here. A sample of carbon monoxide gas occupies 320 liters at 125 degrees Celsius. What temperature will the gas occupy? Will the gas occupy a volume of 1.54 liters if the pressure remains constant? Okay, so let's answer this problem. So So the first sentence gives us the initial state of our gas. So the initial volume, according to the first sentence, is 3.20 liters. And the initial temperature is 125 degrees Celsius. The second sentence will give us the final state. Okay, so the final state, according to this sentence, is it will have a volume, okay, a final volume of 154 liters. So now we are asked to determine the second temperature. Before you proceed, okay, so this is very important. So before you proceed with the calculation, keep in mind that the temperature here should be expressed in Kelvin, not degrees Celsius. Why not degrees Celsius? Because if we have 0 degrees Celsius, for example, okay, whatever the product or quotient is, that will be equal to 0. Okay, obviously that doesn't make sense. So that's why we have to convert the degrees Celsius into Kelvin. And we already know how to do that, right? So in order for you to get the Kelvin, you just add 273.15 to your degrees Celsius. So that means this degrees Celsius, okay, so what's the temperature in terms of Kelvin? So 273.15 plus 125, so that will be 398.15 Kelvin. Okay. So I highly suggest you to include this 0.15 here. Okay. So I highly suggest you to do that. So again, whenever operating with temperatures in the gas laws, you have to convert it into Kelvin. Okay. So with all this information, we can now use the Charles law. So V1 over T1 equals V2 over T2. Since we are looking for the T2, okay, so we are looking for this one, we need to cross multiply this to the other side. Okay. Let us cross multiply it here to the other side. So that will give us this. And this fraction here has to be cross multiplied also to the other side. So this one goes into the numerator. This one goes into the denominator. Okay. So just basic algebra. So it means our equation should be T2 equals T1 V2 over V1. Okay, so again, you just need to recall your algebra for us to be able to get the equation like this from this. Okay, so just recall your cross multiplication. Okay, if that is in the denominator, if you want to cross multiply it, it will be positioned in the numerator after the operation. And if it is in the numerator after cross multiplication, it will now be positioned at the denominator. So with that, we can continue our solving. So let me just copy the equation here. So this T1 V2 over V1. Okay. So that's T2 equals, what's temperature 1? So that's 398.15 Kelvin. Volume 2 is 1.54 liters and volume 1 is 3.20 liters. As you can see, the liters cancel out, okay? And that the final unit that will remain is Kelvin, okay? Again, take note that when you do calculations in gas law that involves temperature, you have to convert them into Kelvin. Okay, so based on my calculator, the answer should be 192 Kelvin. Okay, so that's the answer, 192 Kelvin. But since we are given degrees Celsius, that means we have to convert this into degrees Celsius. Okay, so to do that, all you have to do is to subtract 273.15 from it. Okay, so let's subtract 273.15. So our final answer will be 81.54 degrees Celsius. Okay, so this will be our final answer. Again, if you are given Celsius, you have to express it in Celsius. If you're given Fahrenheit, you have to express it into Fahrenheit. Okay, but keep in mind that whenever you are going to plug in the temperature, it should be expressed in Kelvin. So next one, we have the Gay-Lussac law, or the pressure-temperature relationship. So just like what we did in the Charles law, okay. So as you can see, increasing the temperature of the gas actually increases the kinetic energy of these particles. So that means they will hit the sides of the container more. When they hit the sides of the container, that means they exert force on it. Okay, and exerting force on it increases the pressure. So that's why we have Gay-Lussac law. Okay, and just like earlier, the Gay-Lussac law is directly proportional. Okay, so that means the pressure is directly proportional to increase in temperature. Okay, so again, the logic will still hold true. Okay, that increasing the temperature increases the kinetic energy of gases, making them collide more to the sides of your container. Okay, and as they collide more to the sides of your container, they actually exert force. Okay, and increasing the force exerted by the gases increases the pressure. Okay, so that's why we have here a direct relationship. So again, this proportionality can be converted into an equality by introducing a constant. Dividing both sides by temperature, we get this equation. Okay, so at initial state, initial state, the ratio of the pressure and the temperature is equal to some constant. At the final state of your change, okay, so after you did some change, okay, so we are now at the final state. The ratio of the final pressure and the final temperature is also equal to the same constant. So that means since we have the same constant here, that means we can combine them to form this final equation, P1 over T1 equals P2 over T2, where 1 is the initial state and 2 is the final state after you did the after you subject your gas into some changes. So let's have some exercise here. So let's answer this problem. The gases in hairspray can are at a temperature of 27 degrees Celsius and a pressure of 30 pounds per square inch, right? If the gases can reach a pressure of 90 pounds per square inch, the can will explode. To what temperature must the gases be raised for the can to explode? Okay. So the reason why we don't want our cans, okay, to be heated is that due to Gay-Lussac law, okay, so according to this law, when you increase the temperature of your cans, they actually exert more pressure because the particles in there will possess more kinetic energy. Okay, so there is a great chance of your can exploding at higher temperature. Okay, and that's why you don't want to put your cans, okay, for example, deodorant cans, in open flame, okay, because that will explode. Okay, so as you can see, the changes that are happening here is the temperature and the pressure change. So that means it's Gay-Lussac law. Okay. So again, looking at the first sentence, we will have the information for the initial condition. So the initial temperature will be 27 degrees Celsius, and the initial pressure is 30 pounds per square inch or PSI. Okay. So this can be written as PSI, the pounds per square inch. And according to the second sentence, suppose that your gas could reach the final pressure of 90 pounds per square inch. What will be the equivalent temperature? Okay. So again, just like earlier, since we are dealing with temperatures here, you have to convert them into Kelvin. Okay. So this can be converted into Kelvin by adding 273.15. So 27 plus 273.15. So that will be 300.15 Kelvin. Okay. So since we have all the givens and we are now looking for T2, we can write the Gay-Lussac equation. So P1 over T1, P2 over T2. Okay. So since we are looking for T2, again, we just need to do cross multiplication. So cross multiply the T2 to the other side. You will get this equation. Sorry. And this fraction needs to be cross multiplied to the other side. So the final equation for T2 should be P2 T1 over P1. Okay. So again, just recall your basic algebra so that you can easily cross multiply your variables. So this is the our equation. So let me just copy it again. So that's P2 T1 over P1. Okay, and then we can now plug in everything. Again, keep in mind that the temperature should be expressed in Kelvin. So pressure 2 is 90 pounds per square inch. We don't need to convert that, as the other pressure is also in pounds per square inch. Okay. times your 300.15 Kelvin. So basically, this is just 3 times 3. So basically, that's 900.45 Kelvin. Let me just double check if I'm correct. But it's 300.15 divided by 30. Oh yeah, so 900.15 Kelvin. So that's the final temperature. And again, just as I said earlier, if you are given Celsius, that means you have to express the final answer in Celsius. So to convert Kelvin into Celsius, all you have to do is to subtract 273.15. Right? So you subtract 273.15, 273.15. Okay, so that will give you 627.3 degrees Celsius. Okay, so just to remind you again, when you are given Celsius, you have to report your answer in Celsius as well. Okay. However, when you are calculating using gas laws, you have to convert the Celsius into Kelvin. Okay, because we don't use Celsius in these calculations. Okay, so those are the first three gas laws. So we have the Boyle's law. Okay, so again, let me just go back. So the Boyle's law gives us the pressure inverse relationship with the volume. This can be explained, okay, with an example such as our lungs, okay. So as we inhale, the pressure inside our lungs decreases. So that means the air outside the body will be sucked into the lungs, okay. So that increases the volume of your lungs. But when you exhale, okay, so the pressure inside the lungs actually increase, causing the volume of the lungs to decrease as well, so that extra gases uh, will be exhaled. Okay, then you have your Charles law. Okay, so Charles law is the volume direct relationship with the temperature. So again, why is it direct? Because we know that when you increase the temperature, your gases will possess more kinetic energy, and as they push the container, okay, they will actually increase the volume. And for Gay-Lussac law, so that's the pressure-temperature relationship. So basically, just like earlier, if we have increase in pressure, sorry, increase in temperature, that means our pressure do also increase because our gases exert too much kinetic energy against the walls of the container. Okay. Now, so given our Boyle's law, Charles law, and Gay-Lussac law, we can actually combine them into one entire equation, which we call the combined gas law. Okay. So suppose we have this relationship. Okay. So this is from Boyle's law. Okay. And this one is from the Gay-Lussac law. Okay. So we can actually combine them as. Okay. So let me show you how. So this is from Boyle's law, and this is the thing from Gay-Lussac law. Okay, so if we combine them, we can write it as pressure is proportional to temperature over volume. Okay, so this proportionality, okay, this is the thing. So this proportionality can be converted into equality by introducing a constant K. So we need to transpose everything to the other side. So that will give us PV over T equals K. The PV over T initially, okay, so if you multiply them and divide them, that will give you a constant. And at the final condition of your gas, the PV over T will be also equal to the same constant. So since they have the same constant, that means P1 B1 over T1 is equal to P2 B2 over T2. So this is the combined gas law. Okay, so the combined gas law states that P, V, and T, okay, in the initial and after the reaction, they are all related to one another. Okay, so again, we were able to get this from the Boyle's law, Charles law, and Gay-Lussac law. So let's have this short exercise. Okay, so first exercise here we have um, a small bubble rises from the bottom of the lake where the temperature and pressure are 8 degrees Celsius and 6.4 atmosphere to the water surface where the temperature is 25 degrees Celsius and the pressure is 180 m. Calculate the final volume of the bubble if the initial volume was 2.1 ml. So let me visualize this problem here. Okay. So suppose this is the lake. Okay. So suppose this is the lake. So this is the surface of the lake. We have a bubble here whose volume is 2.1 ml. And the temperature here is 8 degrees Celsius according to the problem, and the pressure here, okay, is 6.4 atm. And obviously what will happen to the bubble, okay, since it is in water, it will rise to the top. Okay, so as the bubble rises to the top, of course the pressure, volume, and temperature should change as well. Okay, so at the top, according to the problem, the surface has a temperature of 25 degrees Celsius and a pressure of 1 atm. So now we are asked what is the final volume. Okay, so that means we need to employ the combined gas law. Okay, so again, the combined gas law is P1 B1 over T1 equals P2 V2 over T2. So keep in mind that this is still a gas law, so that means your temperature should be converted to Kelvin. Okay, so this 25 degrees Celsius needs to be converted into Kelvin, so that will be 298.15 Kelvin. This 8 degrees Celsius needs to be converted as well to Kelvin, so that will be 273.15 plus 8, so that will be 281.15 Kelvin. Okay, so again, it is very important for you to convert the temperature into Kelvin. So now we are going to solve for V2. Okay, so since we are solving for V2, that means these two variables should be transposed to the other side. Okay, so this will be cross multiplied to the denominator. This will be cross multiplied to the numerator. So our equation will look like this for V2. That should be P1 B1 T2 over T1 P2. Since we have all the information given, we already changed the temperature into Kelvin. That means we can plug all the information in the equation. So P1, pressure 1 is 6.4 atm. V1 is 2.1 ml. T2 is in Kelvin, that's 298.15 Kelvin. And our T1 initial temperature in Kelvin is 281.15 Kelvin. And what's next? The P2, okay, the final pressure is in atm. Okay, so as you can see, the units will cancel out, the atm and the Kelvin will cancel out, giving us the final unit ml. So that means our uh, equation or our cross multiplication is indeed correct. Okay, so I will just type it in my calculator because I'm not sure what's the answer. So 6.4, 2.1, 298 divided by 281.15 times 1. Okay, so the answer is 14.25 ml. Okay, so as you can see, the small bubble, which is just 2.1 ml, at the bottom of the sea or at the bottom of the lake, okay, as it reaches the surface, it grew in size. No? So from 2 ml, it turned into 14 ml. Okay, so that's gas law. Okay, so yeah. We are still not yet done. Okay, so we are just halfway through. Okay, so the next gas law is the Avogadro's law, which is of course derived by Amadeo Avogadro, the one who invented the mole concept, right? Okay, so in the Avogadro number, in the Avogadro's law, according to him, the volume of the substance is directly proportional to the number of moles. Okay, so this is obvious, right? Why? Because, for example, in this picture, in this GIF here, this person is blowing air into the balloon. Okay, so by blowing air into the balloon, that increases the number of uh, air molecules inside the balloon. So since there are many gas molecules now inside the balloon, then the volume will obviously increase. Okay. So in the picture here, you have your baking soda, and on the bottom of this bottle, you have your suka. Okay, so vinegar. So as they react, okay, so your baking soda and vinegar can produce carbonic acid. Sorry, carbon dioxide, and that carbon dioxide is collected by this balloon. Okay, so as the reaction proceeds, the number of carbon dioxide molecules increases as well. So that's why the volume of the balloon increases. Okay. So again, basically, Avogadro's law states that the volume is directly proportional to the number of moles. So this proportionality can be converted into equality by introducing constant and then divide both sides by the n. So you will get this equation. So at condition 1, the ratio of volume and mole is equal to some constant. And at condition 2, after you did the reaction, the um, volume and the mole ratio will be equal to the same constant. Okay, so since these constants are the same, then you can combine them. So our Avogadro's law is V1 over N1 equals V2 over N2. So with that, let's answer the next problem. Okay. So this is the question. So actually this one is kinda okay, so this one is kinda tricky. Okay, so anyway, so let's read. A cylinder with a movable piston contains 2 grams of helium. More helium was added to the cylinder and the volume was adjusted so that the gas pressure remains the same. How many grams of helium were added to the cylinder if the volume was changed from 2 liters to 7 liters? The temperature was held constant. Okay, so basically the initial state, okay, so let me just write here the initial state. So you have your 2 grams of helium, and this is the balloon. Okay, so you have 2 grams of helium inside the balloon, and the volume is 2 liters. At the final state, okay, at the final state, okay, sorry, this should be kind of bigger. So the final state, the volume of your balloon, or your cylinder rather, is 2.7. The question is how many grams of helium was added. Okay, okay, how many grams of helium was added. Okay, so just like in stoichiometry, when you are given grams of substance, you have to convert it into moles. Okay, also because Avogadro's law doesn't make use of grams kasi. So that means you really have to convert the grams into moles. Okay, so as you can see in the equation, we don't have grams here. What we have here is the mole. Okay, so yeah, so we have to solve for the mole of the 2 grams helium first. Okay, so we need to solve for N1 first. So we need to solve for the moles of the helium first. So mole helium. Okay, so that's 2 grams divided by what's the molar mass of helium. So let us just round it off to 4 grams per mole. So that means the mole of helium in this container here is 0.5 mole. Okay, so that means instead of writing 2 grams, I will write 0.5 mole. Okay, now since we have the moles, we can use the Avogadro's number, right? So again, what's the Avogadro's number? V1 over N1 equals V2 over N2. We are looking for the final moles first, okay? So we need to solve for the final moles first. So we need to cross multiply this, okay? Cross multiply it to the other side. So that's n2 v1 over n1 equals v2. And then this things here, this fraction here should also be cross multiplied. So the n1 goes to the numerator, the v1 goes to the denominator. So our final equation should be n1 v2 over v1. Okay. So now let us plug in all our numbers. Okay, all our given. Initial mole is 0.5 times the volume final 2.7. Sorry, it should be liters. Initial volume is 2 liters. Okay, so as you can see, liters will cancel out. That means we did the correct calculation. So so that's zero point 0.5 times 2.7, 2.7 divided by 2. So the answer is, okay, so the final moles of helium is 0.675. Okay, so now we are not yet done because the question here asks us about how many grams of helium were added. Okay, so were added. Gano'n daw karami yung dinagdag. Okay, so we need to convert the mole into grams again so that we can compare the initial and the final amounts. Okay, so this mole has to be converted into grams, right? So solving for grams using mole 2. Okay, so G2 is grams 2. Okay, so what's the equation when converting moles to grams? Okay, so that is mole times the molar mass. Okay, so the grams of helium, okay, should be the mole of helium times the molar mass of helium. So that is 0.6, oopsie, that is 0.675 mole times 4 grams per mole. So 0.675 times 4, that's 2.7 grams. Okay, so initially you have 2 grams of helium, and in the final calculation we saw that the grams of helium was increased to 2.7 grams. Okay, so the question is how much helium was added. Okay, so basically you just have to subtract the final mass, okay, and the initial mass. Okay, so that will be 2.7 grams minus 2.0 grams. So 0.7 grams of helium was added. Okay, so that's our answer to this problem. Okay, so again, our knowledge in stoichiometry will overlap with this topic. Now let's talk about the ideal gas law. Okay, why do I have to cover this one? Okay, because remember, okay, that we have the k, the constant earlier. Okay, have you seen any value for the k? Okay, no, we have not seen any values for the k, the constant, right? Because basically what we just did earlier is to cancel out the constants, right? However, in the ideal gas equation, they were actually able to solve for that constant. Okay, so basically, if we combine the Boyle's law, Charles' law, and the Avogadro's law, we will get this equation: PV proportional to NT. Okay, so this is the Boyle's law. Okay, the Vn is the uh, Avogadro's law, and the Vt is the Charles law. Okay, so by combining them, we can actually get that constant. Okay? We can actually get for the value of the k we are solving earlier. Okay, so again, just like what we did in the previous problems, this proportionality can be converted into equality by introducing constant k. But this time, instead of using k, they use r. Okay, Okay, so instead of using K, they use R. Okay, so this R is the ideal gas constant now. So the proportionality constant that we just eliminated earlier, it has now an identity, which is the ideal gas constant, R. Okay. And by derivations, okay, we were able to get its exact value to be 0.08206 liter atmosphere per mole Kelvin. Okay, so that is the constant that was eliminated in the previous discussions. Okay, so yun yung constant na kina-cancel out natin. Okay, so again, the value of R is 0.08206 liter atmosphere per mole Kelvin. So let's have this problem here. 1 mole of methane occupies 20 liters at 1 atm. What is the temperature of the gas in Kelvin? Okay, so given, so according to the sentence, we have 1 mole, so that's N. So 1 mole of methane gas, the volume is 20 liters, and the pressure is 1 atm. Now we are asked what is the temperature. So we know the ideal gas law is PV equals nRT. And since we are looking for the T, we have to cross multiply the N and the R. So that's temperature equals pressure volume over nR. Okay, and then now we are going to plug in all the numbers. Pressure is 1 atm. Volume is 20 liters. N, 1 mole. And the gas constant, that's 0.08206 liter atm per mole Kelvin. And as you can see, atm and liter can be cancelled out, and the mole can be cancelled out also in the denominator, giving us the final unit, Kelvin. Okay, so that means our derivation is correct, and the final answer should be, let me just plug it in the calculator, 1 times 20 divided by 0.8206. So the answer is 243.72. So I will just round it off. 244 Kelvin. Okay, so that's the answer. So again, just keep in mind that the R, the gas constant, has a value of 0.08206 liter atmosphere per mole Kelvin. Okay, so again, that's 0.08206 liter atmosphere per mole Kelvin. So we have several questions here. I'm not going to answer all of them. We'll just answer the first two problems, and then um, later in the video, you can actually answer it. Okay, but I will give you the correct value for these three problems here. So again, I will just answer two questions, this and this one. Okay, and then for the rest, it's up to you to work on with. Okay. So let me just move. Let me just use another application, which is my whiteboard. Okay. So let's use my whiteboard in order to answer these questions. Again, I'm going just to answer two questions. Okay. So that means the rest of the questions, you have to do it on your own. Okay. What's the first question? Sulfur hexafluoride. Okay. So this is our first question. Okay, so the first question, sulfur hexafluoride, SF6, is a colorless, odorless, and very unreactive gas. Calculate the pressure in ATM exerted by 1.39 moles of the gas in a steel vessel of volume 6.09 liters at 55 degrees Celsius. Okay, so again, we are given with the number of moles. Okay, we're also given the temperature, also given the volume, and then we are asked to determine the pressure. So since all four variables are being, three of the four variables are given, that means we need to use ideal gas law. Okay, kasi we are given the pressure, sorry, the volume, the mole, and the temperature. So This is ideal gas law. Okay, so the given again. So let's write given. Um, the mole is equals to 1.39 moles. Okay, and then volume. Okay, so that's 6.09 liters. Temperature is 55 degrees Celsius, and we are asked to look for the pressure. So again, when working with gas laws, you have to express the temperature into Kelvin. So this should be added with 273.15. So that is 328.15 Kelvin. Okay, so again, the temperature should be converted to Kelvin. So now, since we are solving for the pressure, we have to write the ideal gas equation, PV and RT. We are looking for the pressure, so that means we need to cross multiply the volume. So that gives us the equation nRT over V. Okay, so N is the number of moles, which is 1.39. R is the gas constant, which is 0.08206 LATM per mole Kelvin. And the temperature, okay, so let me just move. Okay. The temperature is it should be in Kelvin, okay? So that's 328.15 Kelvin. And then the volume, which is 6.09 liters. So as you can see, the moles cancel out, the liters do cancel out as well, and the temperature Kelvin do also cancel out, leaving us the final unit ATM. That means our derivation was indeed correct. So I will just need to plug them in my calculator. So what's the answer? The answer is 6.15 ATM. So this is our final answer for this question. Okay, so again, everything's kind of easy, okay? So for the next question, okay, so you may want to pause the video if you want to try, and then just play it again if you want to know the answer, okay? Okay, so we are now back, okay? So let's calculate the volume in liters occupied by 5.58 grams of ammonia at STP, okay? So we have this thing called STP. Okay, so STP is the standard temperature and pressure. Okay, so again, STP is the standard temperature and pressure. And the standard temperature is actually 0 degrees Celsius or 273.15 Kelvin. Okay, so that is the standard temperature, and for the pressure, that's obviously 1 atm. Okay, so these are the two standard temperature and pressure: 0 degrees Celsius or 273.15 Kelvin and 1 atm. So basically, if you see STP, you are given two variables already: the temperature and the pressure. Okay, so again, let me just erase this so I can add more space in answering. So given the pressure, according to STP, that's 1 atm. The temperature, according to STP, that's 0 degrees Celsius or 273.15 Kelvin. And what else? We are asked, we are given 5.58 grams, okay? So the grams is 5.58 grams of NH3. And we're asked to solve for the V, the volume. Okay, so let's write the PV and RT. So we are given the pressure, okay, we are given the temperature, we are given the grams. However, take a look, no? So in this problem, we are not looking for the grams. No? We are actually required to give the moles. Okay. And of course, we can easily do that. Okay. So basically, you can just divide your grams by the molar mass, right? So what I will do here is that I will include the conversion in this equation. Okay. So instead of solving for it separately, okay, I will just include the mass mole conversion in the equation. Okay. So again, keep in mind that the mole is equal to the mass over the molar mass. Okay. So this fraction here is the mole. Okay. So the reason why I'm doing this is that so I can eliminate the no, I can eliminate my chances of rounding off numbers. Okay. So let's solve for the volume. Cross multiply the pressure, so that will give us V. So mass RT over molar mass times the pressure. Okay, so again, M, small m is mass, mm is the molar mass. Okay, so volume is equals to, what's the mass? It's 5.58 grams. Okay, R, as you know, that's 0.08206 LATM mole Kelvin. And then the temperature, again, for STP, that's 0 degrees Celsius or 273.15 Kelvin. Molar mass of ammonia. What's the molar mass of ammonia? So nitrogen is 14.007, and then hydrogen is 1.008. So times 3, because you have 3 hydrogens in 1 mole of ammonia. So you just add them up. So let me just use my calculator. Plus 1.008 times 3. Okay, so the molar mass is 17,031 grams per mole times the pressure. So the pressure again, it's STP, so meaning it's 1 atm. So there's so many units, but don't be confused. Okay? So just cancel out everything. So this is grams, that is mole, it's atm, that's Kelvin. So you are left with liters. So that means our operation is indeed correct. Okay. So let me just type it in my calculator. So okay, so the answer, according to the calculator, that's 7.34 liters. Okay, so that's our final answer. Okay, so if you got the same answer, then that means you did it correctly. Okay, so I'm not going to answer the rest, okay, so that I can save time because I have too much. I have so many things to cover pa. Okay. But the answer in number 3, okay, so the answer in number 3 should be 786 degrees Celsius. The answer in number 4 should be 40 liters. And the answer in number 5 is that the final temperature is negative 77 degrees Celsius. And the decrease in temperature is negative 97.7 degrees Celsius. So those are the answers for item number 3, 4, and 5. Okay, so I hope that you will be able to solve for that. Okay, if you were unable to do that, you can ask your instructor to explain you how was that solved. Okay, anyway, I will provide the calculation in Canvas naman. Okay, now let's take a look into the density and the molar mass of the gases. Okay, so the density and the molar mass are actually related. Okay, and we can actually get that from the ideal gas equation. Okay, so remember, our ideal gas equation is PV equals nRT. And just like in the previous problem, I expressed the mole as the mass over the molar mass. Okay, so yeah, so I was able to express the moles into mass over molar mass. We know that the density, okay, we know that the density is mass over volume. So from this equation here, we want to derive the mass over volume relationship. Okay, so I will do it in this blank slide. Okay, so let me show you how it's derived. Okay, so that's PV equals molar mass, RT. So we are looking for the mass over volume relationship here. So that means we need to combine the volume and the mass. So we need to cross multiply the volume. So we will get mass over volume, 1 over molar mass, RT. Okay, so yeah. So I divided both sides by the volume so I can combine the mass and the volume. And anything else that is included on this side should be transposed to the other side. Okay? It should be cross multiplied. So that means mass over volume is equal to the pressure times the molar mass over RT. And this is in turn equal to the density of the gas. Okay, so that is the equation. Okay, so that's pressure times molar mass over RT. So that will give us the density of the gas. Okay, and of course you can also rearrange this. Okay, you can rearrange this. Okay, so density is written in the rho symbol. So this symbol is rho, which is density. So basically, if you want to determine the molar mass from this equation, so let me derive it as well. That's rho, or density, equals pressure molar mass over RT. Basically, you just cross multiply everything. Okay, so you will get molar mass equals density RT over pressure. So again, this symbol here is rho, okay, RHO, a Greek letter which denotes density. Okay, so what's the relationship of density and molar mass? Okay, so looking at the equation here, the density and the molar mass are both in the numerator. Okay, so you can see here. So just like in the previous gas laws, if they are both in the numerator, that means if you increase the molar mass, your density do also increase. So meaning they have direct relationship. Okay. So again, if they are both in the numerator, that means they are directly related to one another. So that means an increase in molar mass will result in increase of density of the gas. So in this table here, we have the different gases and their corresponding um, molar masses in kilograms per mole unit. Okay. Sorry, in that this is in grams per mole pala. Okay. So as you can see, the least in terms of the molar mass is the hydrogen gas, and its density is 0.08. Okay, and then the heaviest among this given is carbon dioxide. Sorry, it's radon actually, and the density is 9.14. So what can you notice is that the lower your molar mass is, the lower your density. Um, okay, while the heavier your molar mass is, the greater your density is. By the way, you might be confused with this term here. Okay, so SP meaning standard pressure. And temperature is not included, of course. Okay, just the standard pressure, not including the temperature. Okay, so yeah, as you can see, the lower your molar mass, the lower your density, and the higher your molar mass, the higher your density. Okay, let's try this problem here. So a 2.1 liter vessel contains 4.65 grams of gas at 1 atm, and sorry, this should be 27 degrees Celsius. So this should be degrees Celsius. What's the molar mass of the gas? Okay. So a 2.1 liter vessel containing 4.65 grams of a gas at 1 atm and 27 degrees Celsius was the molar mass of the gas. So of course you have to tabulate all the given. So the given is 2.1 liter vessel. So that's 2.1 liters. You have your mass of the gas, which is 4.65 grams. Then your pressure is 1 atm. And your temperature is 27 degrees Celsius, or that's 300.15 Kelvin. Okay, you just add 273.15 to it. Okay, so we are asked what is the molar mass of the gas. Okay, so we actually derived that in the previous slides. Okay, so let's do that. So to get the molar mass, that's density, RT over uh, pressure. So are we given the density? Okay, so anyway, so the molar mass is equals to density, RT over the pressure. Okay, so again, what's density? Density is mass over volume. Okay, so that means we can expand it as mass over volume. Okay, so we are solving for the molar mass. We just need to plug everything else here. So the molar mass equals the mass, which is 4.65 grams, R, which is 0.08206, and then your temperature, which is 300.15 Kelvin, volume, which is 2.1 liters, and pressure, which is 1 atm. As you can see, the liter will cancel out, atm will cancel out, Kelvin will be cancelled out, leaving us grams per mole. So that means we are able to solve for the molar mass with this equation. So let me just plug in everything in my calculator. So that's 4.65, 0.0826, 300.15, 2.1 times 1. Okay, so the answer is 54.5 grams per mole. So that's the molar mass of our gas. Okay. So in your quiz and in the midterm exam, you might be asked about the identity of the gas. Okay. So don't worry. The molar mass of the gases will be given naman. Okay. Or actually, you can calculate it. Okay. So if you encounter that kind of problem, so that means you have to solve for the molar mass first, and then from your options, now from your choices, you have to determine which of them will have that molar mass. Okay, so that might appear in your midterm exam and in your quiz 5. Okay, so now let's talk about gas stoichiometry. Okay, so in the previous chapter we were able to discuss stoichiometry. Okay, so basically that's the mass mole relationship, and then you will need to convert your amounts of one chemical species to the other. Okay, so this is the general format of stoichiometry as per your previous chapter. So if you are given the amount of substance in grams, you have to automatically convert it into mole. And then once you have the mole of the substance, you need to convert that into moles of the other substance. And finally, you express it again back into grams. Okay, so now let's try to apply that in terms of gas stoichiometry. So the only thing that will be added in your stoichiometry idea is that instead of just using the grams of the substance, we can also use the volume of the gas. Okay, because the volume of the gas can be converted into moles, right? Okay. How can you convert the volume into moles? You can use the ideal gas equation. Okay, so you can use the ideal gas equation so that you will not just only rely on the mass of your substance, but also you can use the pressure or the volume, okay, to convert that into the moles. Okay, so that's the only thing that will be added here. Okay, so let's try this problem. So let's try this problem. What is the volume of CO2 produced at 37 degrees Celsius and 180 m, where 5.6 grams of glucose are used up in the reaction? So this is the balance equation. We are asked how much volume of CO2 will be produced given this temperature and the pressure. So just like in your stoichiometry, okay, the given substance here, okay, is the glucose. Okay, so you're given 5.60 grams of glucose and you need to convert it to CO2. So because as I said to you last time, so every time you see grams given, you have to automatically convert it into moles. Okay, so that means you need to solve for the mole of glucose. So that will be the mass of the glucose, which is 5.60 grams. Okay, divided by the molar mass of glucose. Let me just calculate it. So that's 180.156 grams per mole. So the mole of glucose we have here is what? 5.60 divided by 180.156. So the mole of glucose we have here is 0.0311. Okay. 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 So yeah. So we were able to solve for the moles of glucose. Now, once you're able to solve for the mole of glucose, then you can convert it to CO2. What will be our stoichiometric relationship? Okay. So looking at the balance equation, 1 mole of glucose will be equal, or it will be equivalent to 6 moles of CO2. So that means we can convert the mole of glucose into the mole of CO2. Okay, how? So in order for you to convert the mole of glucose to CO2, treat this as a conversion factor. So you need to treat it as a conversion factor just like what you did in chapter 1. Okay, so think of it as a fraction that you need to multiply so you can convert glucose into CO2. Since you want to cancel out glucose, it should be written at the bottom. And since you want to get the mole of your CO2, it should be written at the top. So again, I just want to reiterate that stoichiometry is just conversion factor, but a much tricky version. Okay, so yeah, it's like conversion factor. So once you're able to solve for the mole, you have to convert it into the mole of the other substance. The conversion factor or the stoichiometric factor can be obtained from the balanced chemical equation. As you can see, the moles of of glucose can be cancelled out, giving us the mole of CO2. Okay, so what will be the answer? Let me just type it in to my calculator. 0.0311 times 6. So let me just round off the numbers. I will not round it off anymore. Okay, so we now have the mole of CO2. Okay, we actually have an option to convert it into grams by multiplying it by the molar mass of CO2. However, the problem requires us to get the volume. Okay, so from the mole, you are asked to get the volume. That means you have to use the ideal gas equation. So after solving for this, we need to use the ideal gas equation. So that's PV equals nRT. You have the mole of your gas, which is this one. You're given the temperature, which is 37 degrees. Okay, and you are given the pressure, which is 180 m. So that means you can really solve for the volume, right? So all we have to do now is to divide both sides by the pressure. Okay, so just like that. And we can plug in all the numbers. Okay, so to solve for volume, I guess I need to write it here. Okay. So let's solve for the volume nRT over P. So that will be equal to mole 0.1866 mole. R still the same 0.08206 LATM per mole Kelvin. And we have the temperature. What's the temperature again? 37 degrees Celsius. You have to convert this into Kelvin. So 37 to 73.15. So this should be 310. Okay, so this should be written as 310.15 Kelvin. And then on the denominator, you have your pressure, which is just 1 atm. Okay, so let's take a look into the units cancelling. So we cancel the mole, we cancel the Kelvin, we cancel the atm. So we are left with the liter. So that means our equation is correct. So all you have to do now is to just type it in your calculator. So the answer is, according to the calculator, it's 4.75 liters of CO2. So that means by burning just 5 grams of glucose, you will be able to produce 4.75 liters of CO2. Okay, so that just gives you an idea on um, how low the density of gases are. Okay, so imagine just a few grams is actually equivalent to 4 liters. Okay, so yeah, that will give you an idea on how little the density of gases is. Okay. So, there will be supplemental questions. Sorry, there will be supplemental exercises in your Canvas about this. So, um, just wait for your instructor to publish it. Okay, but this is how we do gas stoichiometry. So, just basically apply the ideal gas law when you're asked to convert the volume of gas into moles, or to convert the pressure of gas into moles, and vice versa. Okay. So it will still follow the rules of stoichiometry, but this time you can convert the amount of your gases not only into grams but also in terms of the pressure and volume. Okay, so there will be more exercises on this. So just wait for until your instructor publishes um, the exercises. Okay. So now let's talk about the Dalton's law of partial pressure. Okay. So in 1801, John Dalton, okay, so yeah, it's Dalton, formulated this law. Okay, so according to him, okay, so when we combine all the gases, okay, their partial pressure actually adds up together. Okay, so for example, the reason why we have 1 atm pressure around us, okay, is because 0.77 atm of it accounts for the nitrogen gas, while 0.21 atm accounts for the oxygen gas, and the rest accounts for the other gases. Okay, so that's the reason why we experience 1 atm pressure, because the partial pressure of individual gases are added up. Okay, so that's the Dalton's law of partial pressure. So again, Dalton's law of partial pressure tells us that when you mix gases, their partial pressures gets added up. Okay, so for example, this is the air, which is 1 atmosphere. Okay, so 21% of it is made of oxygen, 78% of it is made of nitrogen gas, and a little amount of argon, water, and CO2 also comprises the decomposition of air. Okay, so that's the reason why we experience 1 atm. Okay, so the 1 atm pressure is not purely oxygen gas, rather it is a mixture of different gases. Okay, so let's try to answer this problem. To a tank containing 2 atm of nitrogen and 1 atm of oxygen gas, we add an unknown quantity of CO2 until the total pressure of the tank is 4.6 atm. What's the partial pressure of CO2? So let's visualize that. Okay, so suppose this is the tank being referred to in the problem. So according to this problem, we add nitrogen gas, which is 2 atm, and oxygen gas, which is 1 atm, and an unknown amount of CO2. The total pressure is 4.6 atm. So what's the partial pressure of CO2? What is this? Okay. So according to Dalton's law of partial pressure, so basically the total pressure is the sum of the partial pressure of individual gases. That is the pressure of nitrogen, pressure of oxygen, and pressure of carbon dioxide. So now we are looking for this. So that means you have to transpose this into the other side. Okay. So the correct equation should be P total minus the pressure of nitrogen gas minus the pressure of oxygen gas. Again, when you transpose this term to the other side of the equation, the sign should be reversed. Okay. That's why we have minus sign there. So total pressure is 4.6 atm minus the pressure of nitrogen gas, which is 2 atm, the pressure of oxygen gas, which is 1 atm. So what will be the partial pressure of CO2? So this is very easy. 4.6 minus 2 minus 1. 4.6 minus 2 minus 1. The answer is 1.6 atm. So that is the partial pressure of CO2. Okay, so that's all. Okay, so that's the basic lang. Okay, don't worry, we will not give too complicated questions about this in the quiz. Okay, so it will just be a very basic question. So now let's take a look into the last part of our discussion, which is on the kinetic molecular theory of gases. This is somehow related in your lecture discussion, which is about the kinetic molecular theory of matter. Okay, so basically, the kinetic molecular theory of gases and matter, they were actually formulated by two physicists named Ludwig Boltzmann, okay, the one on the left, and Scottish physicist James Clerk Maxwell. Okay. So they were using the properties of gases to determine the motion. Okay, so that's what they did in physics. So in their findings, they were able to make generalizations about the behavior of gases, and those behaviors are given as postulates for the kinetic molecular theory of gases. You don't have to memorize this, but you have to be familiar lang. Okay. So according to them, okay, according to Boltzmann and Maxwell, the kinetic theory of gases are the following. So according to them, we assume that the gas are separated from one another and their distances are far apart. Okay, so they are far apart. Okay, so that causes the gas to have low density because the particle distance is so far. Okay, so that means they will occupy greater volume. And also, gas molecules are always in constant motion and they are random and they may frequently collide with one another. Okay, so and then when they collide against us, that actually exerts pressure on us. Okay, then the next one is that the gas molecules exert neither attractive nor repulsive forces from one another, meaning that they may not combine, okay, or they will not repel. Okay, so that means they are just virtually not interacting with one another. Okay. Then lastly, the average kinetic energy of the molecules is proportional to the temperature of the gas. Okay, so that means the higher your temperature is, the higher your kinetic energy is. If you want to determine the average kinetic energy of your gas, you need to use this equation. So that's K equals 1 half m u square, wherein u is the gas speed. Okay, the u is the root mean square speed. Okay, so the root mean square speed is actually the measure of the speed of gases, and according to this equation, the speed of gas is inversely proportional with the square root of its molar mass. Okay, so again, the speed of the gas is inversely proportional to the square root of your gas. Why do you think is that? Okay, the logic here is this. Okay, if your gas is so big, okay, if it has a high molar mass, then obviously it will be harder for it to move, okay, because it possesses greater potential energy. So that's the reason why there's an inverse relationship between the speed and the molar mass of your gas. So that means the lighter your gas is, the faster it will go, but the heavier your mass is, the slower it will go. Don't worry, we will not give you problems about this, okay? So the trend is this, okay? So the bigger the molar mass, the slower the speed of your gas particle, and the higher your temperature, the faster your speed, the faster gas particles go, okay? So the picture here on the left shows the temperature effect to the speed of the gas. At 100 Kelvin, the average speed of the gas is somewhere here. However, as you increase that, the average velocity also increases. Okay, so 300 Kelvin, this is the average speed, and at 700 Kelvin, this is the average speed. So that means if you really increase the temperature, the speed of gases increases. Okay, and also according to the molar mass we just discussed earlier, so the heavier your gas is, the slower it becomes, okay? Because it possesses more kinetic energy. So, for example, here we have chlorine gas, which is 70 grams per mole, compared with helium gas, which is 4 grams per mole. As you can see, the helium's average speed is somewhere here, while for chlorine, it's somewhere here, okay? So that means the lighter your gas particle is, the quicker it is, okay? And again, do not worry, we will not give you problems like this in the quiz and the midterm exam. So we just want you to focus on the gas stoichiometry, the gas laws, gas density, and the Dalton's law of partial pressure. So that ends our discussion on kinetic molecular theory of gases and basically gases in general. So um, that means we are done for the midterm period. So expect that we will give you a quiz on this maybe next week. Okay, and then your professor may actually ask you to give you some outputs, especially some problems and practice quizzes. So you have to answer them. Okay. Also, we will be syncing in your Canvas some exercises that will be supplemental to your study about this topic. If you have questions, do not hesitate to ask your instructor. And with that, thank you for listening. And we will see you again after the midterm consultation week, which is on October 25. Okay, so see you after several weeks. Okay, so I hope that you will have you learned something today and you will ace your exams. Okay, so thank you and goodbye.